The next aspect of buffers is the buffer range, the pH range over which a buffer can maintain more or less a constant pH. When we considered buffer capacity, we noted that the larger the concentrations of each of these components, the greater the buffer capacity, the greater amounts of the acid and the base that can be potentially absorbed with minimal pH impact. When we make a buffer in the laboratory, we choose a weak acid conjugate base pair that has a pKa close to the desired pH. And that's because in order to get the exact pH we want, we tweak the relative concentrations of the conjugate acid to its base. And that dials in the exact pH of a given buffer. So again, we choose a pKa of our conjugate acid that's very close to our desired pH, and we tweak this ratio a little bit in order to dial in our pH of the buffer. If we don't choose a pKa that is close to our desired pH, we end up having to manipulate this ratio too much and end up with an ineffective buffer. Let's move on to this problem. Okay, and in this problem, we're asked to make a buffer solution with a targeted pH of 10.00. We're asked to use a carbonate bicarbonate weak conjugate acid-base pair because the pKa of our bicarbonate is very close to our targeted pH. The pKa of the bicarbonate ion is 10.328. Stated another way, if we had a balanced bicarbonate carbonate ion buffer containing equal concentrations of each of these ions, its pH would be equal to pKa, which in this case is 10.33. We want to adjust our ratio to bring our pH down to 10.00. And here we've translated the Henderson-Hasselbalch to this specific application. We want a targeted pH of 10.00. This is our pKa value. So what we need to do is to tweak this ratio of the base, which is a carbonate ion, to the acid, bicarbonate ion. We need to tweak this ratio to make this equation true. So stepping through, we subtract 10.328 from each side, and we know that our log of the ratio of these ions has to equal negative 0.328. Solving for the numerical value for this ratio, we see that it needs to be 0.47. In this next step, we've calculated the amount of the carbonate ion needed to achieve the appropriate ratio. So we have our carbonate ion multiplied by 1 is going to be equal to our bicarbonate ion multiplied by 0.47. This bicarbonate ion concentration is given in the question stem, or the statement of the question. If we look up here, we see the bicarbonate ion concentration is 0.2 molar. So we can substitute that in and get a numerical value for the needed carbonate ion concentration. All right, so we get our actual value for the needed concentration of our carbonate ion in order to achieve the desired pH. Now we want to calculate the amount of sodium carbonate that we need to add in order to achieve that concentration. Now we look up to our question statement and we can see that we have 1.5 liters of the buffer. Stated another way, we want to add enough sodium carbonate to this 1.5 liters of the buffer in order to increase the concentration of our carbonate ion to this value. We can calculate then the number of moles of sodium carbonate that we need, and from there, the mass. All right, so here we have multiplied our desired concentration of the carbonate ion in moles per liter times the liters of solution, and then all that remains is to multiply this by our formula weight of sodium carbonate. To get the mass of sodium carbonate that we need. And this mass is equal to 14.944 grams, or with 2 sig figs, 15 grams. Let's do a little sanity check. Use a Henderson-Hasselbalch. We know that the pH is 10.328, and we said that if we had a ratio of 0.094 to 0.2, we would have the right pH. So this is 10.328. If we work this out on our calculator, this comes out to be a negative 0.328. So we do indeed get a targeted pH of 10.00. Let's review what we did here. Okay, we're looking for a buffer with pH 10. We chose a weak conjugate acid-base pair whose Ka is relatively close to the targeted pH. And then we determined what ratio is needed in order to dial in the appropriate pH. And then we're able to calculate the desired concentration, and from this desired concentration could calculate the actual amount of sodium carbonate that needed to be added to 1.5 liters of 0.2 molar sodium carbonate in order to achieve the buffer.